Hello again, everybody. Today we're looking at 6.5, exponential growth. So again, we're looking at exponential equations, just like this one right here. Y equals a b raised to the x. Now, just in this case, we're looking at b being kind of like a 1 plus r type situation. But we'll get into that in a minute. Let's start by just looking at what exponential growth is. An exponential growth happens when a quantity increases by the same factor over equal intervals of time. All right, so basically what it's saying is a certain thing or a certain moment or event can be modeled exponentially if it's increasing by the same factor over time. So let's take a look at this formula now, and let's break it down into what each thing, technically is going to mean for us when we're looking at these situations. R. Let's start with R, just because it's probably the simplest one to remember, because R stands for rate, and that rate of growth. And that's going to be that same factor that we were just talking about. Again, T, I think, is going to be an easy one to remember, because most of the time when we see T in an equation, it stands for the same thing, and some of you might already know what that is, which is time. Time can also be a very difficult thing to place into an equation, because sometimes time is represented in days, sometimes time is represented in years, months, hours, minutes, seconds, so you have to be very, very careful in placing time into an equation. But we'll see that in an example later. Now let's look at y and a. A is going to be our initial amount. So in the other equation, we had a being our y-intercept, which again, that makes sense. The y-intercept, the time when x equals 0, so initial time, that's our initial starting point, our initial amount. And y. Y is going to be our final amount, what we're going to get out of this. We're going to put in an initial, give it some sort of rate to grow, and a certain amount of time to grow, and what we'll get out as our output will be a final amount. Now let's take a look at all of these things in action. Right, in example 1, we are using exponential growth function that says y equals 150,000 times 1.1 raised to the t. And it represents attendance at a music festival after so many years after 2010. So let's look at what these things break down to. Y is our final amount. So over a certain amount of time with this growth rate, how many people are going to this music festival? This number right here, 150,000, that's our A, that's our initial amount. So that's in 2010, how many people went to this music festival. T we have up here representing time, so the amount of time after 2010 if we're looking for a certain year. And this in here is a combination of 1 plus R. So this 1.1 is not the rate. This 1.1 is 1 plus the rate. Okay, so that's important to remember. So our first question is, by what % does the festival attendance increase each year? All right, well, I was actually kind of just talking about that when we were talking about this piece in here being 1 plus the rate. When I'm asking by what % does the festival attendance increase, that's asking what is that rate of growth. So that should be our R value, which I know 1 plus R in this equation equals 1.1. That's where I'm getting that from. So if I were to solve this equation, I would subtract 1 on both sides, and R would equal 0.1. As a percentage, 0.1 is 10%. Right? We move the decimal place over 2 places. It was here, we move it over to the right 2 places to get the percentage out of 100. How many people will attend the festival in 2014? Round to the nearest 10,000. Right? So we are given an almost cryptic version of what time is in this case. All right? We're not necessarily given how many people will attend the festival 4 years after it started in 2010. So what is the attendance at t equals 4? But it's said in a different way. How many people will attend the festival in 2014? We were told this equation starts in 2010. We're looking for 2014. So that means that our time equals 4. All right, another thing that we have to be careful about when it comes to time is that, yes, this is 4 years from when it started. But does this equation model time using years? Or does this equation represent time in months or weeks? We have to make sure. And if I read it again, at music festival, t years. It does represent it in years, so I don't have to worry about changing this 4 years into some other representation of time. I can just keep it as a 4. So let's take a look at what we have to do. I want to find out the final amount, how many people, from this equation. That's wrong. So 150,000 times 1.1 raised to t, and in this case t is a 4. Alrighty? So when I evaluate this, I do 1.1 raised to the 4th power times 150,000, and for something like this, perfectly reasonable for you to use your calculator. You will get 219,615. So what does this mean? It means that 4 years after the festival started in 2010, so that means in 2014, 219,615 people attended. Remember that this says round to the nearest 10,000, so 10,000 place would be right here. Rounding to that means that we're rounding to 220,000. Try and do part B on your own, and we will take a look at that in class. All right, once you've done part B, we can move on to a different type of exponential growth equation, which is a compound interest equation. All right? Basically, what this is growth that happens so frequently that we assume that it's happening in particular moments in time. So we can talk about this in terms of things like money in a bank, which I think is the example that we're about to go into. And what they do is they will accrue certain amounts of interest at certain periods in time. So it might be that we're going to check how much money you have at this point and accrue interest every single week. Every week we're going to accrue interest, or every single day we're going to accrue interest, or every year we will accrue interest. So the growth depends variably on how many times you compound it, how many times you look at it and apply the formula. So let's take a look at what all the pieces of this formula mean. Y, again, is going to be the number that we get out, that final. In this case, P is one of those ones that's going to be easy to remember because P represents principal amount. And that's another way of saying initial. R, again, is going to represent the rate. T is going to, again, represent time. But we are going to introduce a new variable to the equation, which is n. And n is going to be the number of times interest is compounded per year. Okay? Number times compounded. Okay, and we're going to hear that word a lot, compounded. Let's look at example 2 and see how all of these things play out together. You deposit $100. That's important. Into a savings account that earns 5%. That's important. Annual interest compounded yearly. That's important. Write a function for the balance after so many t years. So what this tells me, it gives me a lot of information just in a very, very short amount of time. It tells me I deposit $100. That's principal. That's initial amount of money. It tells me I earn 5% interest. That's rate. That's how much it's going to grow. It also tells me that it's going to get compounded yearly, which means that my n value, which means how many times that interest is going to get applied, is 1 time every year. Writing a function for the balance after t years. This last sentence tells me what my variable is. This last sentence tells me I don't have a value for t. T is what makes this an equation rather than just an expression. So, y, final amount, equals principal, which we said was 100, and then a big parenthesis, 1 plus the rate, which we said was 5%. Now be careful not to put a 5. It's 5%, but if you remember back to the other example 1, that 5% was written as a decimal, which means 0.05, over n, the amount of times compounded per year. So it says I'm compounded yearly. That means it compounds 1 time every year, raised to the n1 times t. And that is our equation. Now, part B asks us, we deposit $500 into a savings account that earns 4% annual interest compounded yearly. Write and graph a function that represents the balance y in dollars after t years. Do me a favor, try B on your own. Remember that there are important pieces of information here: the initial deposit, the rate, how many times it's compounded per year, and what t represents. Okay, try that out and we'll take a look at it in class. Alright, once you've done that, we're ready to move on to the last example, which is going to show a real-life application of these types of things. What we have here is a table that shows the balance of a money market account over time. Right, so a money market account it's not so intense as you going into the stock market and exchanging on your own, but it's essentially a place where you can put money and hopefully gain on that money. So basically we have 0 years initial balance, after 1 year the amount that's in the account, after 2 years the amount, after 3 years the amount, 4 and 5. Okay, what we want to do is write a function for the balance after t years, after maybe I want to find out 20 years, after maybe 16 years. But we want to be able to create an equation so that I can easily figure out how much money will be there after a certain amount of time. So, what do we need? Well, I know that the equation I'm going to be using is going to look like final amount equals some amount that I initially put in times 1 plus the rate, all raised to the amount of time I put it in. But I still need to fill in all these variables. What is A? What is R? So right off the bat, I think I actually might have even said it already, we know that A, the initial amount, is 100. How do we know that? Because this says the time in years is 0, which means that no time has passed and I have $100 in there. That means initially, right at the beginning, I have $100. So I know that my function is going to look like this at least. 1 plus, and then I don't know r. How am I supposed to figure out what r is? What is the rate of growth here? Well, going from 100 to 110, what does it look like I'm doing? What factor would I have to multiply by to get from 100 to 110? Or 110 to 121? 121 to 133? It looks like I'm taking 10% of 100. 10% of 100 is 10. And that's what I'm adding on here. It looks like I'm taking 10% of this and adding it onto here. So it looks like my rate is 10%, which, written as a decimal, rate is going to be 0.1. So when I go into my equation, I can write 0.1 raised to the t. Very nice. Now I can actually simplify this a little bit, just so it looks a little bit nicer when I graph it. Y equals 100, and I don't need 1 plus 0.1 in there. I can do 1.1, add them together, raised to the t. All right. Now, let's graph it. Let's see what it looks like. Let's make this graph so that this is 25. Let's make this 50. Let's make 75, 100, 125, 150. I don't want to write all of these in here because it'll get a little too confusing. But each time, each block, I'm going up 25. Let's make that the scale for the y-axis. And over here, I'll just do 1 year, 2 years, 3 years, 4 years, 5 years. Alrighty. So, what do I have going on here? I have 0 and 100. I have 1 year and 110. I have 2 years and 121, which is almost 125. I have 3 years, 133. 4 years, 146, which is almost 150. 5 years at 161. So there is an upward slant to this thing. It's just not going up as steep as one might hope, especially if you're investing money. But that's the type of equation that we have going on.